Gresham College presents Citius, Altius, Fortius, Records, Medals and Drug Taking by John D. Barrow.
Well, welcome to this first lecture of 2012 in my Maths and Sports series. And today we're going to talk about a collection of topics all related to sort of being successful by fair means or foul, and mathematical aspects of records and sequences of performance at the Olympics. The title, if you're not a Latin scholar, Citius, Altius, Fortius, faster, higher, stronger, is the Olympic motto. It has a curious origin. The founder of the modern games, Baron Coubertin, went to school in Paris, and a local school to the one he went to, not his own school, had this as their motto, and he rather liked it, so he just snatched it from the neighbouring school and used it as his Olympic motto. Well, if you want to be successful in the Olympics, let's have a look at who's been the most successful individual in the history of the Olympics. So what I've done here was just to gather some data from reference books on the people who have won the most medals at the Summer Olympic Games, and I've distinguished and separated medals that are won in individual events from medals that are won in team events. You can see, obviously, there are certain sorts of events which, if you're desperate to win an Olympic medal, it's good to be in. So if you're in swimming or you're in athletics or other team sports, there are many more medals on offer than there would be for an individual event alone. So what's shown in this table, here are some names. I'll identify some of them in a minute. And here's the pattern of gold, silver and bronze medals won in individual events. And here's the total number of individual medals. Some people think that you shouldn't just add them up, but it's better to win a gold medal than to win a silver and a bronze. And so you'll find in many medal tables some type of weighting or scoring is applied. So you might be given 3 points for each gold medal, 2 for each silver and 1 for each bronze. So if you apply that rule and calculate here, you've got 9 3s plus 1 is 28. If you include team medals as well, you get a new total, 16 for Michael Phelps. And if you weight the whole total, you get a new grand weighted total. Who are the people on this list? Well, Phelps needs no introduction. He'll be in London later this year, probably winning some more gold medals. American swimmer. He's the most successful Olympic athlete of all time in terms of number of gold medals won. So 14, if you include the relays, and 9 individual gold medals. Of course, lots of the events are really rather similar. If you win the 100 metres freestyle, you might well be expected to win the 200, and you might win the 50 as well. Mr. Uri won't be known to you. He won his gold medals back in the 1900s in the long jump, the high jump, and the triple jump, and those events were standing jumps in those days. So he was only in individual events. He won the gold medal in every event that he competed in, and all 8. Kaslavska was a great Czech gymnast from 1956, 60, 64 era, specialist on the beam exercise, and she's the most successful in terms of gold medals. If you keep going down, you'll find somebody else who vies with Phelps for being the most successful Olympian, and that's Latinina, another Russian gymnast who has a huge total of 31 individual medals and 41 if you include, 14 medals and 18 if you include the team events. So again, she's in the 56-64 period. But if you introduce these weightings, you see it makes a difference. Although she has 4 more medals than Phelps, if you total up and you introduce the weightings, she falls behind. Here's the top athlete. It's Carl Lewis, individually, including the team. More gymnasts Andrianov and Shaiklin, and there's another runner here, Nurmi, with 6 gold medals. He's managed to get some team medals because back in his day there were team events in the athletics, like cross-country events and so forth. If you look for the first British entry in this list, if you keep looking down, keep turning the pages over several times, you can guess who you first find, and it's Steve Redgrave, but he's in 57th place on this list, and he's got 5 golds and 1 bronze, and here are his totals. So this is what you're aiming up at the top. Well, of course, winning certain sorts of medals, particularly team medals, it really helps to be in a big country with a large population. Helps even more if that big country has a big budget, a big GDP, and it spends a good deal of it on sport. By a long way, the most successful country ever in sport at Summer and Winter Olympics per head was the old East Germany. So this was a state that really focused its activity, its international affairs, on being successful in sport, with a state-organised, almost compulsory system for people who turned out to be talented in sport. And we know retrospectively, and suspected at the time, that it was massively and systematically drug-aided. So here are a group of pictures that show what happens if you were to plot the number of medals. This is the logarithm of the number of medals, so this is 10 to the power 4, 10 to the power 3, against some other measure of a country's investment in sport. So this is a measure of what happens if you take into account the population and you also take into account the financial investment. And you can guess what ought to happen. There ought to be more medals if you have a bigger country, you've got more people to choose from, and you would expect to have more medals if you invest more money. But if you combine the two, you find the best fit for recent Olympics, I think this is not the last one, it's the previous 2 or 3, is to a sort of weighted combination of population and GDP. And this straight line here, okay, is the best fit to the data for the major countries, and you can pick from it a number of things. So you can see the USA leads the all-time medal list, and then there's Russia, and then there's China, there's UK here, but there's really a very big variance here. So most of the countries lie some way away from the best fit line. If we convert this best fit line to something a bit more recognisable, what the rule is, if you measure the population in millions and the GDP in billions of US dollars, there's this approximate power law. So the number of medals is proportional to the population to about the 0.7 power times the GDP to about almost 0.3. If you pick one games where you might, at random, let's pick Barcelona, and you play this game with the weighted medals, so you give a score of 3 times the gold plus twice the silver plus the bronze, then you have a simple and rather sort of impressive formula for the score. The 1/3 power to quite high precision of the population times the 2/3 power of the GDP. Now, if you just mess around with this a little bit, you can see if we take the cube root outside of PG squared, and if you just defined another s, let's call it s dashed, to be a half of s cubed, so that we can cube both sides, then s primed is a half PG squared. And that's a formula that, if you've done any mechanics, is rather reminiscent. It's rather like the kinetic energy. Half times the mass times the speed squared is the kinetic energy of motion of a body of mass m at speed v. So this is one of the sort of econophysics analogues that people talk about in mathematical economics, that half PG squared is like the energy of a nation, the economic and financial energy. And you can go on and play other games with these formulae, but you can see roughly the number of medals won is linked to this energy of the nation. Well, you might think it's a rather bad thing that medal success is so strongly a function of GDP, of money. And if you were a journalist producing medal tables, you might want to therefore regard the success of a country in the Olympic Games medal-winning business as being the extent to which they are above this standard curve. So this standard curve is what you expect simply from your investment in your population. And your degree of success is the extent to which you are above this line, and your degree of failure will be the extent to which you're below. Well, this issue of money being a big distorter of performance is something that we recognise in this country, particularly in football. So the Premier League is not really very competitive after you get below the first 3 or maybe 4 teams. So a team like Liverpool at the moment is closer to being relegated than it is to being at the top of the table. And one of the reasons this is, of course, that there's a sort of Matthew effect. You know, unto he who has shall more be given. That if you have lots of money, you buy more players, you get more revenue, you buy even more players, and there's a runaway instability. And it's amusing to look at what happens in another country where they try to directly counter that effect in sport. In the USA, there is a system known as the draft, and it's used for American football, and it's used in basketball and other sports. And what it amounts to is that at the beginning of each season, when new players become available to be hired by the top teams, then there is a selection of those players. They put themselves forward from college to be offered contracts by the top teams. And the US system is that the team that came bottom of the league in the previous season gets first pick. So the worst team gets to pick the best player, and so on down the ladder, and eventually the top team that won the cup final the previous year gets the last pick. And this selection process is fairly easy to model with a simple type of delay differential equation, as it's called. So your rate of success this year is proportional not to your state of play at the moment, but by the state of things as they were at some time in the past. And what that does is to produce a performance prediction that's oscillatory. It goes up and down like a sinusoidal wave. And when you look at the results of American Football League performance, if you give people sort of a point for winning and half a point for drawing and none for losing, you'll find that over a period of 8 years, 4 times the delay time in setting up the draft system, teams do indeed behave in this sinusoidal way. So they improve for a period of years. This puts them at the bottom of the draft, and then they go down for a bit, and then they come up. So in American sporting politics, this is something presumably that's agreed by all the participants. They wish to do it. In Europe, it would be contrary, of course, to employment law to do that. Again, it would have to be something that people agree to take part in. But it's an interesting example of how you can have a rule system that actively attempts to prevent rich teams getting more and more and more advantage. In the American Soccer League, for example, there's another factor rather like this. All teams are required to travel in economy class. There can't be any private aircraft to convey team members to matches. So if you're a very wealthy club, you can't be being ferried around by private jet while your opponents are checking in to the American equivalent of sleazy jet or whatever. Well, suppose you do want to invest in some way, you want to spend your fraction of GDP What should you do if you want Olympic success? And if you look back to what happened with China in particular in the run-up to Beijing that they were hosting, there was an enormous increase in investment, and to some extent there has been in this country before the last games and the current ones. What should you do if you want to get more medals for your buck, as it were? Well, the first thing is that you should pick sports that not many countries do. Okay, so if you pick cycling, you've got a much better bet of winning something than football or the 100 metres in track athletics. You should maybe also pick events with lots of relays, lots of team awards, maybe things where there are double bronzes. So in boxing, for example, once you lose a bout, you can't fight another one. So the two losing semi-finalists both get bronze medals. So there's more medals on offer in these sort of fighting events than in other sports. If you pick sports where there's a lot of inter-event similarity, you're going to get more for your money. You can see this effect particularly in sports that Britain is good at, like sailing and especially cycling. It's not a fair comparison to compare the performance of the cycling team, given a certain amount of investment, with that of the athletics team. Athletics is like many, many completely different sports. So what you do to help the pole vaulters won't help the marathon runners or the hurdlers or the middle distance runners. But in cycling, there is a very big shared element. So if you invest in aerodynamically superior bikes, better kit, better velodrome training facilities, it will benefit everyone in your squad. The other lesson perhaps we learn, there are certain sports where sheer training and organisation and discipline can win you Olympic medals over pure talent. So if you looked at the last Olympics, China invested in all sorts of things like sort of women's weightlifting, various types of team event, where systematic squad training, improving pure strength, something that can be done very systematically, really pays off. Whereas if you decide you're going to invest in trying to have the men's 100-metre sprint champion, there's such a big talent factor required that just by searching people out and training them systematically, you're probably going to fail. A lesson we haven't really learnt in the UK, it's not necessarily a good lesson to learn, don't try and do too many sports. Okay, so if you go to Kenya or to Ethiopia, anyone who's fit and has very good cardiovascular system will be doing distance running. So there is a great specialisation of fit athletes into a small number of sports. Here, all the throwers, the shot putters, the hammer throwers, the discus throwers that we don't have are playing rugby. They're playing rugby league, they're playing rugby union, they're in a host of other sports. So you dilute your pool of talent for any particular sport if you do a very, very wide range. All the American long jumpers, high jumpers, strength event people are enormously reduced by the enrolment of very athletic, very powerful athletes into American football and to some extent also into basketball. The other thing that you could do to try to counter this is that you've got to encourage some people to change events. So if you have lots of 400-metre runners all thinking that they're going to get the last spot to make the team at 400 metres, some of them need to be encouraged well beforehand to think about competing at 800 metres. More radical, you might try to encourage people to change sports or to join a different sort of sport. And the sort of sport that you might join and the factor that you might think about, something like triathlon. See, the triathlon is massively biased, and so a certain sort of sports person should consider seriously whether they should take up the triathlon, and certain other sort of sportsmen should perhaps consider whether they should give it up. Here are the results from the last Olympics. If you're not familiar with the triathlon, it's a sequence of 3 events. So you first of all swim, and you then cycle, and you then run. And you have a transition, okay, so you come out of the water, you put your cycle shoes on, and you get on your bike with your horrible little withered toes from swimming 800 metres in the sea, and you then ride for an hour or so, and then you jump off your bike and you run 10,000 metres. And so the times are just added up. The distances that are spent on each of these sections are a historical accident. The event derives from something called the Ironman event, which was first competed for in Hawaii, I think, back in the early 1970s. It was the brainchild of the San Diego Track Club. And although that event involved much, much longer swims and runs and cycle rides, the proportion of time spent on the run, the ride, and the swim have remained the same. And even in shorter sort of mini triathlons, the same proportion is adopted. But if you look at the results at the last Olympic Games, you see that it's not really very cleverly chosen. So here are the medalists at the last Olympic Games in the men's, and here are the women. So you were swimming for 18 minutes, and then you're cycling for 59 minutes, and then you're running for 30 minutes. Your overall time is about 1 hour and 48. These were the fastest legs on each of those. Women, the times are sort of 1.5 minutes slower on the swim, and about 5 minutes slower on the bike ride, and about sort of 3 minutes and a bit on the run. But you can see that there's about 54% of the time is spent cycling, 16% swimming, and 28% running. There is a massive bias in this event to cyclists. It's really just a cycle ride with a warm-up run and a shower. So if you're thinking of changing events to the triathlon, you're a swimmer, don't bother. But if you're a cyclist, and you can swim a bit, and you can run a bit, everybody can get better at running. Not necessarily at swimming, because you might have a bad technique. But you can see that a certain type of transformation, change from one event to this event, could be very advantageous. Well, because of this, I suggest a revision of this event. So a logical, equitempered triathlon would be one where competitors spent essentially an equal amount of time on each event. So to do that, let's take the 1 hour 48 as some type of standard. Then what would you want to do? 1.5 kilometre swim, okay, probably just a 40 kilometre bike ride and a 10 kilometre run. That's what you do at the moment. But to get those time stages roughly equal, around 36 minutes, you're looking at a 3 kilometre swim. Triathletes will not like that. 24 kilometre bike ride and a 12 kilometre run. So that's what the triathlon should be like, and if it was, there would be an equal appeal to swimmers, riders and runners, and you would end up with a rather different type of competitor. It would be attractive to a different type of sports, multi-event sports person. Well, you heard it first here. So this event is interesting because the times are added directly. You just keep going. It's like a relay with one person in it. But there are other multi-event sports where you convert performances into points. I came across, and one is the Decathlon, and I came across this on the web, this rather amusing poster for the 100 litres, the front crawl, asymmetric bars, rowing, weightlifting, the individual pursuit, the shot, and the 3-day event. Yeah. But the real Decathlon, a formidable event. It didn't, I think it existed in the first Olympic Games, and then it wasn't in the second one, but then after that it resumed. It involves, as the name suggests, for men it's 10 events, for women it's the Heptathlon. Jessica Ennis is one of the prime competitors in that event. So what do? Well, you've got a mixture of running, throwing and jumping. So you've got to sprint 100 metres, you've got to hurdle 110 metres, sprint 400 metres, and then snag around 1,500 metres at the end. You've got to throw the shot, the discus and the javelin, and you've got to high jump, long jump and pole vault. And the women have 200 and 800 metres, I put that in twice for some reason, 100 metre hurdles, high jump, javelin and shot put. And the interesting thing about this event is that you don't just add the performances, but the performances are converted into points. And there's clearly some arbitrariness, there's some mathematics really involved in that. And here's how the scoring works in this event. You've got two sorts of goals. For the events where the outcome is a time, you want that time to be as short as possible. Where the outcome is a distance, you want it to be as long as possible. So in the field events, where you want the distance achieved in a jump or a throw to be as long as possible, the mathematical formula that's used to convert performances to points looks like this. So it's some quantity, let's label it A, times the distance minus another quantity, all to the power some number which we'll call C. So if your distance is less than B, then you're not going to get any points at all. So that's the sort of the rock bottom. On the track, where you should get more points for having a smaller time, formula has the same type of pattern, some number times another number minus the time to the power C. And for each event, the International Athletics Federation, time to time, decides what these quantities should be, A, B and C. There's one for every event. And they're arrived at by looking at all performances, historically and currently, in that event, the world record in that event, and also the performances in decathlons, which are sort of biased in a slightly different way, as we'll see. So, for example, the A's and B's are not terribly fascinating. Okay, they're just numbers that come from the averages of the performances. What's more interesting is this number up here, C, which sits in the power. And if this number was just equal to 1, then the point system would be rather neutral, in that if you were better, you ran faster, you threw further, you would find it just as hard to win the next 100 points as you'd found to win the previous 100 points. But if C is bigger than 1, then you're going to find it harder to win the next 100 points, to be better than you did to win the previous one. So you get more reward, as it were, for the better performances. If C is less than 1, then you get comparatively less reward for the better performances. Well, if you look at the tables, there's a pattern to what goes on. If you look at the running events, the statistics have ended up giving values of C for the running events here, here, and here. They're really quite similar, values of C. They're about 1.8. Okay, it's quite close to 2. If you look at the jumps, which I've put in orange here, long jump, high jump, pole vault, which is a little bit different, again you can see they're quite close to 1.4. So there's another cluster for the jumps. And then if you look at the throws, this is quite close to being neutral. They're very close to 1. Now, the interesting thing about these events is that clearly you can see that if we tinker with these tables, if we change these numbers, we're changing the reward system for different sorts of points. So if we were to change these throw values of C and increase them up to 1.8, we'd be giving massive reward to the better throwers. And the results of the whole competition would be different, very different. In fact, when Daley Thompson won the Olympic Games in Los Angeles, he just missed beating the world record by a few points. But a few months later, the tables were recalibrated, and he was suddenly told that he was now the world record holder because his performance in Los Angeles had given him an increased score on the new tables, and he had beaten the world record by a few points. So this is an event with a serious type of subjectivity. And if you look at the women's heptathlon, the pattern is really very similar. So for the values of C for the running events around 1.8, for the jumps around 1.35 to 1.4, and for the throws quite close to 1. So it's the same for male and female. So let's have a look. What sort of things could you now examine? Well, the world record in the decathlon for the 10 events is 9,026 points. It's a fabulous score by Roman Sebrele from the Czech Republic, and the number 2 all-time performance is not many points behind by the Czech number 2. Well, if you wanted to score 9,000 points, which I can guarantee will win you the gold medal in London, what would you have to do? If you wanted to score 900 points in every event, this is what would do it. And you can see some of the performances. I mean, they're not by any means out of this world. 10.83 for 100 metres, 48.19, 400 metres, under 18, under 19 schools, top-class competitors run faster than this, much faster than this. So a 15-year-old runs fast as this in England. 1,500 metres, 4 minutes 7. Do that bouncing around on your head. I mean, people 15 years old can run much faster than that. But in the throws and the jumps, the performances become rather more impressive. So for a good class competitor competing at a high level in national or even county championships, these individual performances are not really out of reach. But it's being able to put them all together over 2 days, 5 events per day, that's clearly very, very challenging. Over here is a picture I've created of where did the 100 best performances in the decathlon ever, how did they get their points? So how were they spread over these events? And that should say 400, not 4,500. So what you can see from this is then what the top decathletes tend to be like. They are not 1,500-metre runners, and they don't bother much preparing for 1,500-metre running. They're mostly enormously heavy, strong athletes. It's quite a challenge to run around 1,500 metres, although Sebrele runs 4 minutes 20 or something, very, very fast. But you can see long jump, hurdles, sprints. They tend to 400 metres, they tend to be sprinter, jumper type athletes. And also you might say from this picture, if you've got limited amount of training time, where should you invest it? Where will you get more points per hour of training? And you can see that in these jumps, sprints, hurdles, you will get much more in return than spending all your time pole vaulting or cross-country running for the 1,500 metres. Because sprint training will help you in the long jump, it'll help you in the 100, it'll help you in the 400, it will help you in the hurdles. So it's a particular sort of athlete who is going to be successful in the decathlon in the way that the point-scoring structure is set up at the moment. Well, I thought I would try to invent a new point-scoring scheme, which we'll call the Barrow Score, or the B total. And it's an attempt to see what happens if you avoid all this points transformation, subjectivity. And in the decathlon, we've got 6 events, the jumps and the throws, where you want to have a larger distance as possible. And you have 4 running events where you want to have the smallest time possible. So why don't we just multiply the distances achieved in the jumps and the throws together, convert them all to metres so they're in the same units, and divide by the times all in seconds. Okay, so you will have an answer that's got units of meters to the power 6 divided by seconds to the power 4. But it's a very simple system. It's very direct. It's not without biases, of course, and at your leisure you can think about what happens. I won't put all the arithmetic in, so we're just multiplying the distances together, dividing by the times, and if we look at the world record holder, Sebrelé, he seems to come out on, not in first place anymore, but second. And the number 2 in the world, Dvořák, who scored 8,994 points under the old system, he's the top-ranked athlete under this new scheme with 2.40, and Sebrelé at 2.29. But it's interesting that one captures sort of exactly the same two people. You end up with a number that's neither sort of 10 followed by 50 zeros or vastly smaller than 1. It's a perfectly sensible set of numbers to be dealing with, and it's a much more direct, subjectivity-free way of converting performances into points. And you can think about what sort of performance here would boost this score the most. So where is it easiest to shorten a time or increase a distance? They're all equally weighted. Well, obviously, the longer you're running for, the more chance that you've got to decrease that time. The event that's got the longest distance that you're throwing has got the most scope for increasing that distance. Well, before we leave the decathlon, there's some sort of funny facts and observations about it that's interesting. That one case that people have made is that you should have C equal to 2 for all the events, because this is rewarding people in proportion directly to the amount of that kinetic energy. Remember I mentioned previously half mv squared, so the amount of work that they have to do in each event energetically. And if you do that, it of course does change the scores a lot. And again, Mr. Dvořák becomes the new world record holder with a very large 9,468 score. This change really helps the throwers, because at the moment their value of C is 1.1, but it will go all the way up to 2. Point I mentioned here, let's get some sort of normalization here. The present world record is 9,026. Suppose you set the current world record in every event, okay? What would you get? You'll get 12,500 points. And you can see, therefore, the world records must have played some part in standardizing things, because it's a nice round number. If you took the best performance that had ever been achieved in a decathlon, then you're up at 10,485. And as for individual events, if you try to convert Bolt's 100-meter world record, he gets 1,202 points for that. The fastest ever 100 meters in a decathlon, on the other hand, is much lower, 1042. The best world record of all on these tables is the discus world record from long ago, and it scores 1383. Well, I want now to sort of have a look at records in another far simplistic way, really. And first of all, to show you that a simple statistical analysis can tell you whether records are being set randomly or not, whether there's something else going on. And mathematicians have a simple set of arguments for analysing how often you expect a record to be set in a sequence of events which are random. So this might be the rainfall, high tides, or something like that you had some suspicion was random. So suppose in the first year or the first period where activities took place, you're doing the event for the first time, so it must be a record. Okay, so after 1 year, the number of record years, record seasons, is obviously 1. In the second year, things are independent of the first year. You've got a 1 in 2 chance of beating the record that you set in the first year, and a 1 in 2 chance of not beating it. So after the first 2 years, the expected number of record years is just 1 plus a half. If you go to year 3, then the performances that you could have from the first 2 years could have 6 possible rankings. So the performance from year 1 could be better than year 2, could be better than year 3, or year 1 could be best and year 3 second and year 2 third. So these are all the permutations of 1, 2 and 3. And you can see that there are just 2 of the rankings here which produce a record in year 3, and that's this one and this one. So this one produces a record in year 2, this is a record in year 1. So there are 2 of those, 6 possibilities, 2 over 6 is a third. So the chance of a record in year 3 is 1 in 3, a third, plus a half, plus 1. If you keep on going, same sort of argument, after 4 years, the extra factor is a quarter, and so after n years, the expected number of record years is just going to be the series 1 plus a half plus a third plus a quarter and so on, plus 1 over n. So this is the famous harmonic series that we've seen in these lectures before, and as we know, if we keep on going forever, this series sum can be larger than any number that you specify, but it grows very, very slowly. Okay, so if we call the sum after n terms h of n, then after 1 term it's 1, after 2 it's 1.5, and so on. After 4 it's 2.083. But even if you add in 100 terms to this series, the sum has only grown to 5.19. If you go to 256, it's 6.124, 1,000, 7.49, and even 1,000,000 terms. The sum is only 14.39. So roughly, good approximation, the sum is quite close to 0.6 plus the logarithm, natural logarithm of the number of terms. So from this you can begin to see how many records you might expect to have. So if you were looking over 100 years, since 1900 or so, and you took a rain check each season in athletics, you would expect there to have been 5 records in each event, 5 world records in the last 100 years. If you look at the number of Olympiads, okay, there's about 26 of them, summer games, since they began. You would expect only to have 4 records set in any event, if record setting was just a random process, rather like the rainfall. Of course it isn't, because here's just one example. Here's the men's 100 metres, and here are all the records, the times there have been a world record since about 1910, right up to the present. I haven't counted them all, but there's vastly more than 5. So the setting of sporting records is not a random process. Okay, it's driven by improvements in training, improvements in facilities, in track surface, in timekeeping even, starting technique, and things like that. However, there's something rather odd about world records in athletics. And the first approximation, there aren't any women's records anymore. Certainly not in events that have been competed for the last 30 or 40 years. So this is a great problem for sponsors and meeting organisers, people who want publicity and excitement. You're never going to get a world record in the 100 metres, the 200 metres, the 400 metres, the throws, and so on. So here, for example, here's all the standard events on the Olympic programme. Here's the date of the last world record in the men's event, and here is the date of the last women's record. And I've highlighted some events that seem to have had recent world records, but which don't really count because they're events that were only invented a few years ago for women. So these events weren't taking place back in the 1980s and 90s. So women's world records stand for a very, very long time and look usually completely unapproachable. So nobody gets anywhere near, say, the women's 400-metre record, which is down around 47.4 seconds, something like that. Whereas if you ran 49.4, you would be the favourite for the gold medal at the Olympic Games. So what's going on here? Well, if we just take the numbers from the previous picture, there are 11 women's world records which are more than 20 years old, compared with only 2 men's records. And the problem is that you're looking back to an era when drug taking was systematic, particularly by East German athletes. We know from the records which have become public after the fall of the East German state, there was systematic doping and performance enhancement. And those records really are a result of that regime, which can no longer continue because drug testing became much more stringent, and these very old records all tend to predate the time when drug testing for male growth hormone and other drugs that favour improvements in women's performance became sort of essentially impossible really to use without detection. Well, drug testing is an interesting little mathematical problem, and it tests one's sort of logic and understanding of rather simple statistics. And the principles at work there are really the same ones that need to be at work in the court system if you're trying to determine whether a piece of evidence, say DNA evidence or fingerprint evidence from an individual is really a decisive piece of evidence for their conviction. So let's just do a simple example. Let's suppose that 1% of athletes take performance-enhancing drugs. So I'm just picking these numbers so that they make the arithmetic come out reasonably clearly. And 80% of drug tests which are performed detect the presence of drugs. But 9.6% of those tests give you a positive result when no drugs are present in the athlete. So these are false positives. So what's the situation? So we can make a little table here that 1% of athletes take drugs, 99% don't in your sample, and your test will find 80% of those to test positive, therefore 20% will test negative, 9.6 will test positive if they don't take drugs, and 90.4% will test negative when they don't take drugs. So you've got 9.6% giving you false positives, and you've got, over here, you've got 1% of people taking drugs testing negative. So these are the sort of false negatives. So what you're interested in here is that suppose you test positive, okay? What's the chance that you did actually take drugs? So how effective is the test? Well, here are the numbers again. 1% of people took drugs, 99% didn't. So what's the chance that you test positive here? Well, there's 1% of you to start with, and there's an 80% test rate. So 0.008% of true positives result from this test. But the 99% people who don't take drugs, there's a 9.6% that they give a false positive. So 9.5% of this sample end up giving a false positive. It's very large. Down here, if you test negative, well, there's 1% of people who took drugs, and the test fails to identify because 20% of the tests are bad. So 0.2%, 0.002, give a false negative. So these are people who take drugs, but the test doesn't find them. And then over here, we've got true negatives. So these people are not taking drugs, and the test correctly identifies that. There's 89% of those. So what's the chance that a drug tester tests positive? Well, it's the 0.008, the true positive, divided by all the positives. So 0.008 plus the false positives. So the chance that a drug user tests positive is 0.0776. That's not very high, 7.76%, even though the test is 80% correct. So the reason this number is so small is because of this very large number of false positives, 9.5%, so bigger than the number of positively tested drug users. So this is the type of statistical analysis that you have to make in order to determine how effective a particular test is at finding true drug takers. And you can see that you can play around with these numbers. You perhaps don't know what these numbers are at all, because if people are not being detected, they're successfully evading drug detection, then you just don't know about them. So you're just biased to the people who do detect. And then you can try and work harder and do better at making these numbers better and this number bigger. But the basic logic of what you have to calculate is essentially the same. It's an example, if you know any statistics, of course, of the Reverend Thomas Bayes' famous theorem from the 1700s. So Bayes didn't publish this during his lifetime. It was found by one of his colleagues and published after his death. So he considered the general problem of if you want to know the probability of some outcome given some other condition, how does it depend on the probability of that condition given the outcome times the probabilities of the two possibilities. So here what we've just worked out is a special case of this. We want to know what's the probability that you've been taking drugs, A, given that you test positive, B. Well, it's the probability that you test positive given that you've been taking drugs times the probability of taking drugs over the probability of testing positive. And in the court system, where this would be applied to DNA evidence or something else, the prosecutor will try to fool you, if you're a juror, into thinking that PA given B is the same as P given A. It's even known as the prosecutor's fallacy. And so if we just went through the arithmetic and we put all our numbers in, P of A is 1%. This is the effectiveness of the test, 80% down here. This is the false positive probability, B not A. And this is the probability you're not taking drugs. Put all the numbers in, we get the answer that we just got by our slower application of pure thought, if you like. But this is the general formula that Bayes found, very, very important formula of statistics, which can deal with any of problems of this variety. Well, the last thing I want to talk about is a situation where an unfair advantage can be gained, sometimes not deliberately, as in the case of taking drugs, where there's an interesting little piece of mechanics involved. And this is race walking. So these are the sort of people walking along in a rather unusual style. Here's a picture of the 1908 Olympics. This is White City. This is the start of the men's 3,500 metre walk. Almost everybody seems to be lifting at the start, but I think they didn't worry about that. Well, race walking is not like walking down the street. So race walking looks different, okay? See people waddling along, swinging their hips. How does walking differ from running? In everyday life, the point about running is that your centre of gravity bobs up and down. So it doesn't move in a straight line, it moves in a sort of sinusoidal line. When you walk, your centre of gravity moves pretty much in a horizontal line. It doesn't bob up and down. If you're a race walker, there's a more stringent definition of walking that you have to adhere to. And here's an official statement of it. Looks as though it was amended by the bracketed condition at some stage. And what has to happen is that you have to maintain contact with the ground with one foot all the time. So your next step, your foot must not come off the ground there at the back until the front foot has touched the ground. So you must have continuous contact with the ground. Whereas running, of course, you're jumping up in the air, you are not in continuous contact. The other requirement is that your back leg must be straight. So your joint at your heel must lock out. So you can't walk with a bent leg in the way that you do when you run. So this runner has always got a bent leg. So this is the rule, a progression of steps, so the walker makes contact with the ground, okay, and the back leg, second rule is that the back leg must be rigid. The point about this rule is that it's visible to the human eye. Nowadays, where people are scrutinized by television cameras and even private videos, this is a very difficult criteria to adhere to. The human eye is like looking at something with a camera that just takes a shot 25 frames per second. It's a really rather slow camera, whereas the video cameras and TV cameras that are looking at walkers are taking many, many more frames per second than that. So they see things that you don't see, you can't pick up with the naked eye. So here's a sort of an action cartoon here of a race walker sort of adhering to this. Let's have a look at a couple of shots. So here's an international race walker. He's clearly lifting. Okay, so the rules are, by the way, on these events, 20 kilometres and 50 kilometres on the road, you're allowed 2 warnings. Okay, so you get sort of 2 warning cards shown to you by judges round the course, and for lifting or not straightening your leg, and the third one you get, you're out, you're disqualified. And there are cases at major championships of athletes being disqualified just a few metres from the finish in the stadium. And you have to get the warnings from different judges, so it can't be the same person that's always giving you a warning of the same thing. So this fellow here, you see, he's clearly breaking contact. This film is rather slowed down. His leg is straight, but he is breaking contact. The next video, this is the star man. He's no longer active, so he was the world record holder, Olympic champion. And you can see his style is absolutely perfect, and certainly to the naked eye, he's not lifting. And the way you get these fantastic speeds is to have extremely high cadence rate. So his step rate is very similar to that you would have in a 400-metre sprinter. And this is what requires tremendous leg strength. Now what I want to look at is, let's just look at the mechanics of the forces involved to see if we can work out a criterion for when you lift. And I've got 2 pictures to do this. So if we imagine that this is the centre of our walker, here's his weight going downwards, and this is where the back foot is, this is the stride length, this is the leg length, and that back foot then has a reaction, a force going upwards from the ground as you change this angle. And if that reaction force were to go to 0, then the athlete must be lifting. If it's positive, must be lifting. So by working out the equation of motion in the vertical direction, so r upwards minus mg is equal to the acceleration in the vertical direction, and also looking at the rotation around this point, so the acceleration of this angle times the moment of inertia of the body is equal to the moment of the weight that's causing the force. So if we do this, what we find is that there's actually a very simple criterion for whether this force can ever go to 0. And what it tells you is what's the maximum speed, what's the maximum rate at which this angle can be turned, and therefore the maximum linear speed that a walker can achieve. And it's given by this formula here. It depends on the leg length, depends on the stride length, leg length, and the acceleration due to gravity. So if we sort of write it rather bigger here, and we put some numbers in, leg length of 1 metre, stride length of 1.3, then the maximum speed that you can achieve without breaking contact is only about 1.7 metres per second. But the top walkers, we've seen, like Mr. Perez, they're going faster than 4 metres per second over distances of up to 20 kilometres. So this is not mechanically possible without breaking contact. And this simple calculation just shows you that. Well, you could say, what could you do finally to try and make things worse? Well, you could reduce your stride length. Okay, so if you make S smaller, you take a smaller amount there, and you get a bigger V. But you can't make it much smaller than the leg length, okay? And there's a limit to how small you can make it. Instead, what you do is to effectively increase your stride length by swinging your hips. So that's why walkers swing their hips and walk in this unusual style. It's a way of artificially lengthening your stride by increasing adding a distance in here, so your stride length becomes much bigger than it would have become if you didn't swing your hips. So if you do this, what you find is that you might increase your leg length a little bit, but you still can't get anywhere near the 4 metres per second speeds that are observed. You would have to have a leg that was 2.3 metres long to do that, or your hip sway would have to be about 3/4 of a metre. So you would have to have a very unusual physiology indeed. So this rather simple analysis tells you that there is lifting going on here, but it might not be terribly dramatic, and it might only be perceptible by really quite high-speed photography. So I've overrun by a little bit, but I hope I've given you a few different insights into some aspects involving sort of records and what you can do to gain an advantage, both fairly and unfairly. Thank you.
For all information, please visit www.gresham.ac.uk.